Hello, welcome everybody. I hope you guys are safe, enjoying the weather, whatever we get, and ready for your exam on Monday. Right? I'm excited. I know I'm probably the last one who's being excited here. Nobody else is, so we'll get started in about 4 minutes or so. In the meantime, if you have any questions regarding, topics or whatever, just make sure you put it in the chat. I'm gonna be actively monitoring that, and yeah, we'll get on with this, and hopefully get you pumped for the exam on Monday. You guys can keep all the thanks for later, okay? You guys are very welcome. Don't worry. I'm glad I was able to help, so that's nice. Any particular things that's bothering you guys in this material? Because the content, in my opinion, is easy, but yeah, we'll of course cover all the things that we talk about. But I don't see any particular reason for like getting stressed. Recursions are easy. We can talk about them. And I have some special things planned for you guys here. So I have some questions which I feel that they haven't really covered or paid attention to enough. Okay, and those are the typical questions that show up on the exams too. Okay, so I'm gonna show those to you. I have solutions to them as well. I'm gonna try to tell you how to use the tools that you are allowed to use to its maximum potential, and save ton of time in the exam, right? So that's my plan for today. So optimization is something that I'm gonna focus on. Yeah. So the study guide that I'm gonna be making that right now with you guys. Okay. I'm gonna try to tell you what you need to know, and just kind of condense thoughts. Okay. I personally feel like having a study guide at this moment before the exam will not be that beneficial, because you are not going to have enough time to follow along in depth with all of that thing. Okay, so this will be treated as a review where I'll tell you exactly what you need to know. You can put them down, you can make your notes if you want. I'm going to be putting them on the screen as well. But my overall attempt here is to make sure I basically optimize your approach to this exam at this point. Okay, and this is being recorded. Of course, I'm not using the Zoom recording, so don't worry about it. I'm using my own external recording. So it will be up there. But you won't really have much time to watch the recording because it's literally just like a day before the exam, right? So I want to make sure everybody who can make it should make it to the meeting. And just want to make it, beneficial for you guys.
Meeting, and I'm still doing other stuff, prepping for the meeting. Hmm? Yeah.
Don't worry, I took care of it. It's okay. It happens. There's a lot of people, and I don't by no means I want anybody to be muted or something. Okay, I will be more than happy to talk to you guys, but as long as you don't disturb people around you, that's all good. Okay, just waiting for one more minute before we start, just to make sure, give everybody time, because I'm always late to my meetings, so I want to make sure everybody has their time to make it in. Does anybody have trouble with differential equations? Finding equilibriums, finding solutions. I think that is pretty understandable. But if you have any questions regarding that, we'll go over those too, because those were I'm focusing on that thing. I personally feel you shouldn't be too worried about recursion, okay? Because the one I want to make sure is like
they're exponential functions, except for u of 0
the recursion itself is just going to be something that might be asked in multiple choices. Okay, so we have to don't stress out too much on that. Mostly word problems. I'm expecting a word problem on optimization, and a big question on either differential equations or extremas. So we want to make sure we're gonna do that. Yeah. So I'll develop like all those algorithms that you're missing, just kind of like having a thought process to solve a problem, and get on with this, right? Okay, let's get started. I'm just gonna try to have two different colors. That's good. Awesome. Okay. So let's start our discussion by talking about recursions, because that's an easy topic. I can get done with it. I can just, leave it out of the window. It's not going to be a big deal. Yes. And you can ask me questions here too, all the time. I'll be monitoring the chat. If I skip over something, please remind me, and I'll be trying my best to make sure I keep an eye on it, okay? So recursive equations. That's a very skinny pen. I need to make sure it's a little bit bigger. So recursive equation basically are able to define equations and next data values using previous data values, okay? So let's say I am going to try to define a recursive equation for you, and what I'm going to do is, yeah, so if you want to share your screen for a lecture question, I will let you do that explicitly after I'm finished like talking about stuff. And yes, we'll have a lot of time to talk about questions, okay? So let's get on with this, right? A recursive equation is basically an equation that uses previous entities to define something. Okay? So here I'm going to try to talk about a recursion. I'm going to say my a of n plus 1, which is the next term, an n plus 1 index, is going to be just equals to my previous number plus 5. Okay? And then I also say that my first initial number that I'm going to starting off with is going to be, let's say 0. Okay? So this way, if you have this definition of a recursive equation, all you need to know is that the next number, a of n plus 1, will be defined by picking the previous number and adding 5 to it. This is a fairly simple recursive equation, okay? And the way I know it's a recursion because we know that the next entity depends upon the previous one, okay? Excuse me. And now, moving on, we would have, if I want to write the terms like A1, A2, A3, A4, and so on out of this, I can try to use this relationship to find those. A1 was just going to be A of 0 plus 5. That would just mean 0 plus 5 because A of 0 is 0. That will be just 5. Here, to find A2, now you will use A1. And A1 we already found out was 5, so it'll be 5 plus 5. That's going to be 10. And then quickly you'll be able to figure out what's happening here because it'll be just 10 plus 5. So it'll be 15. And A3 plus 5 will just be equals to 15 plus 5. That is 20. Okay, so we're trying to make sure that we have enough, ideas here and numbers to kind of quantify this data. Okay, so remember how we're making this is these numbers depend upon previous numbers. And after all, they're going to be discrete numbers, okay? That's why when you're trying to have this, you'll have a sample of data. It won't be a function. It is not a continuous, equation which specifies every single data point. It only takes those discrete values and give results for those particular discrete values. Like in this case, I pick up this, then I'll have the next version this, then that, then that. I do not know that this is not defined for all the values, right? Yeah, so if you want to solve a recursive equation, it could have different meanings, right? They can ask you to tell them what's happening, like what's going on with this recursive equation. So the first basic idea is to just have those numbers there and you can see them and you can give them the numbers. That could be one possibility they can ask you for. The graph of a recursive equation is always going to be a discrete graph because it's not defined for all the values that you have. It's only defined for the real numbers, okay? So keep that an eye out. If you were to plot this data, right? If I was to plot it here, so I can pick up these values, it'll be 5, 10, 15, 20. They all have an increment of 5 as you go, right? So we want to make sure that we understand this is just the nature of what these things are. Now, the toughest question possible on a recursion equation is as follows, okay? So there is no particular solutions to a recursion equation. The recursive equation gives outputs which are numbers, and those numbers form a sequence. Okay, these numbers, if I have put them in a bracket, 5, 10, 15, 20, this is the output of a recursive equation, right? The output of this recursive equation is just going to be a bunch of numbers, which we call sequence in terms of math. Okay, that's how we kind of like define this context. Very easy, straightforward. You can move on. The toughest question they can ask you is to give them a general formula for this recursive equation. So how do you go from a recursive equation to a general formula? I'll show you that next. Okay, so let's say you have a of n plus 1 equals to a of n plus 5, given that the initial value starts at 0. Okay, so now what I'm trying to do is, if I ask you this question, if I ask you what's going to be a of 100, how would you guys answer that question? Just out of curiosity, if somebody has an attempt on it, how would you want to answer this question? If I ask you what's the 100th term in this recursive sequence? Yeah, that's a of 99 plus 5. That's an excellent answer, but you need to know what a of 99 is in order to find a of 100, isn't it? Right? I see a lot of people answering this. So the idea that I'm actually going towards is to find these numbers, you always have to have the previous quantity present there. But what if I don't want to do it? What if I want to see an expression which just literally takes the n value that I'm plugging and gives me the number? Okay, that could be found out by looking at a general pattern what this is doing, right? So yes, as you said, it will be 5 times n, but I'm going to arrive to that expression just by, analyzing the data. Okay, so the first term we all know is 5. Second term will be 10. And third term will be 15. A fourth term will be 20. And da-da-da-da all the way, right? So what I need you guys to see is look at the pattern that's between this subscript, that the value we're looking at, and the actual value we get out of that thing. So for 1 it's 5, for 2 it's 10, for 3 is 15, for 4 it's 20. So by eyeballing, there's no other way. By eyeballing, you can say it's just going to be the a of n is going to be 5 times n. So literally, the expression for the nth term that you want to get out of this is going to be 5 times n. And this is not a recursive equation. Can anybody tell me why this is not a recursive equation? It's not n plus 1. The reason why it's not, yes, it doesn't depend upon the previous answer, okay? Like in this case, you see a of n plus 1 was dependent upon a of n. It was dependent upon the previous term. But this is just solely dependent upon n. It's not dependent upon the previous values exactly, right? So now, with this given fact, I can easily find out a of 100 by just saying 5 times 100. That's just 500. Okay, so that is probably the toughest question you can ask, right? All the general equations that you want to find out, like a general expression, has to be done this way. So you put out the information with the indexes and come up with this. Because you see why I'm doing that is because I want to know how these numbers depend upon which index I'm looking at, okay, or which number of term I'm looking at, right? Once I have that idea, I know I can just literally take that number and, compose my final answer with this. Yes, this is lecture 6. Okay. So keeping that in mind, we have to generally come up with this relationship and just try to form out what's happening, right? So now I'm going to try to define another recursive equation for you guys and see if you guys can get a better idea of this. Okay, it's not too tough, trust me. Don't overcomplicate things. It's very easy. As difficult, that's how difficult it's going to go. Okay, so don't worry. Now I'm going to define another recursive equation where a of n plus 1 is now just going to be twice of a of n. Okay, and I'm going to choose my a of n value to start at 1, or a of 0 particularly to start at 1. So does everybody see why this is a recursive equation? My first question. Right? It's clearly given that it's dependent upon the previous term. Nice. So everybody sees that. Everybody's on the right track with me. Awesome. Now, if I want to find a general expression for this, the method I told you is to try and write out some numbers and see some patterns. Okay? So what I'm going to do is if I write the A1 that will be 2 times 1, which is going to be 2. A of 2, that will be 2 times 2, that's going to be 4. Okay, A of 3 will be 2 times 4, which is going to be 8. And then A of 4 is going to be 2 times 8, that's going to be 16. And I can just keep on going forever. Okay, but I don't really need to go there. Now the next step is to actually look at this index, okay, and try to find the relationship of that index with that number. Exactly. Somebody already guessed it, so they're pretty smart. Okay, nice. Here I see that whenever you want to find a number, you know, like for 1 it's 2, and then for 2 it's 4, and then 3 it's 8, and then 4 it's 16, I can come up with this expression that the general formula for this, A of n, okay, is basically 2 to the power of n. Right? All I'm doing is just raising 2 to the power of that number, and I'm getting the result out of this. Does everybody see that? It will be a little bit hard to see, no problem, but after I told you, you guys can understand and contemplate why it's 2 to the power n, right? Because the numbers I'm getting is 2, 4, 8, 16, so it's basically just going to be, you know, 2 to the power of whatever index I'm looking at. So here, if I ask you a question, what's going to be A of, you know, 60? Then all you have to do is just literally take 2 to the power of 16. That's the answer. Right? So that's the most they can probably ask you. Okay, on recursive equations. And that's just about it. Okay, so I would recommend you guys going over the study guide, and I think there are solutions posted on the YouTube video by a professor that goes over all those things to just make sure you understand what's going on with this new perspective. And you don't have to really stress about what's going on in this particular chapter, in my opinion. Okay, and that's just a good 15-minute talk on recursive equations. That's all you need to know, in my opinion. Okay, does anybody have any questions regarding this? If not, we can move on. Okay, that's good. I'm seeing a couple of no's. Perfect. Let's move on. Okay. The next thing you're going to be tested on is basically what I used to call calculus tools. I know if some of you guys have watched a video on my channel regarding calculus tools, where I have already talked about, you know, the idea of what calculus tells you, you know, to get to those expressions, right? So I'm going to try to just draw a tree diagram here, and try to show you what I'm trying to get to. So function that you're working with, from pre-calculus, you know how to find its domain, range, and like the asymptotes, the intercepts, and all that. Okay, that's something that they expect you guys to know from pre-calculus, and it's okay if you don't, you know, have a fresh memory of that, so don't worry about it. But a function, we're going to be figuring out two things about it. Okay, and we're going to see what it's doing, and the second thing is how it's doing what it's doing. Okay, in very simple words, we're going to try to like break it down this way. So the question comes in like from this, where you have, is it increasing? Is it decreasing? And then you would ask, you know, does it have a max? Or does it have a min? So all these questions that you have, both of this could be either global or local. I'll go over those in just a second. Okay. This is what questions we can ask about a function. Is it increasing? Is it decreasing? Does it have a max? Does it have a min? Yeah, I'm starting on basically covering up the extremas and all the way to like inflection points optimization, and then we'll move on to differential equations. Okay, so I'm not pretty sure exactly what chapter I'm looking at right now, but this is all what you need to know. Okay, so the questions of what about a function is like this, and then you have to think about how it's doing it. Okay, so you say, how is it increasing or decreasing? Right? So that's the next question that follows up. For the what's of this function, you will use the first derivative. Okay? The first derivative of a function will help you extract that information about a function. Okay? And the hows of a function will be given by the second derivative. This is very naive way of layman words that I'm using here. Okay, of course, there are more concrete definitions and stuff for this, and I'm just trying to like paint a picture of what's happening. Okay, so if I was gonna start at a function, let's say I have I can start with any function that you guys are looking at. Some people pointed out that there's a negative this function here times t to the power 9 divided by 2, right? I guess this was from your study guide that you had this problem. So to figure out where this function is increasing, decreasing, having a maxima, minima, how does it concave up, concave down, and where does it have an inflection point, all of those questions are going to be answered by using derivatives. Okay, so if I ask you where is this function increasing, okay, so of course the answer for this, it will be an interval answer because this function could be increasing at a multiple values of t, right? So I'm not gonna like sit down there and specify each value of t where it's increasing, so it's better to just specify an interval where I feel this function is going to be increasing in. Okay, and how do I find that? The rule to find where it's increasing is literally just finding where this derivative is positive. Okay, so now to talk about the derivative where it's positive, we need to figure out the derivative first. And to do that, that's where you have to make sure your prerequisites for this particular exam are there. You need to know differentiation rules in this case, okay? I'm going to try to do the derivative here, where I'm going to rewrite the function like this. I'm going to write 1/2 times e to the power negative t over 2 times t to the power 9. Okay, so I'm going to treat them like this. Two functions that are being multiplied, so I'm going to use product rule. The derivative by product rule will be the derivative of the first function, keeping the second function as it is, plus keeping the first function as it is, times the derivative of the second function. Okay, that's the product rule, and I'm going to expand this. This would need chain rule, as the exponent of this exponential function is not just x. In this case, negative t over 2, right? So the derivative here will be half e to the negative t over 2 times negative 1/2, because derivative of negative t over 2 is going to be negative 1/2 times t to the power 9 plus 1/2 e to the negative t over 2, and derivative of t to the power 9 is just going to be 9t to the power of 8. Yes, the half is going to be counted as a constant. That's why it's just chilling there. I never really touched it. You want to do product rule for a constant, it will not help you at all, because after all, it's just going to be a constant. So my approach is always to just don't touch the constant. Let them stay where they are. Okay? Ignore them for the process of the derivative. This negative 1/2 came from? Is that what you're asking for? The one from the start was actually from the whole given question. So it was e to the negative t over 2 times t to the 9 divided by 2. I wrote them like this, so that I can always keep that 1/2 outside the whole picture. Okay? Saying x divided by 2 is equivalent to saying half times x. So that's why this could be written like this. Okay, hopefully that clarifies your question regarding this. Right? Moving on. So that's the derivative, and now we have to do some algebra to kind of see what picture we're looking at in this case. What I'm going to do is I'm going to factor the 1/2 e to the negative t over 2. Okay, so 1/2 e to the negative t over 2 comes out here, so you'll be left with just basically 9t to the power 8 minus t to the 9 divided by 2. So that's the expression we're looking at. And now we only have to figure out where this expression is positive, because the answer we're looking at is to figure out where the function's increasing. Okay? To figure that out, I just have to see where this is positive, and I can move it on to the next page to make sure I have some extra space to work with. So to test this particular function, I have to see what's happening here. It's basically a multiplication of two terms, okay? The first term being half e to the negative t over 2, and a rule of thumb that you always should remember, that exponential functions is always going to be bigger than 0. No matter whatever t value you plug in, exponentials are always going to be positive. So half times an exponential will always be positive too. So this particular term that we have at the front does not change the sign of the whole function's derivative. So the only thing that changes the sign of a function's derivative is this term. Okay? And we have to see where that actually changes the sign. So now the actual way that you would do it on an exam is first of all find a critical point. So you have to figure out where this function's derivative is actually 0. So you'll find the critical point by setting it equals to 0. And you'll have half e to the negative t over 2 with 9t to the 8 minus t to the 9 divided by 2. Okay? Yes, it doesn't matter. Whatever you have in the exponential will always be positive. Doesn't matter if it's a negative number or a positive number. Okay? The output of the exponential function will always be positive. So like in this case, now I'm setting it equals to 0. Because I'm setting it equals to 0, I know I can factor some extra stuff out of the bracket to make it in this way. So half t over 2, and then you'll have, I can factor t to the power 8 out of this, and I'll be left with 9 minus t divided by 2 equals to 0. Okay, so now I'm looking at this expression, I see 3 factors. Yes, so if there was a negative in front of the term, like here, if I put a negative here, of course, then it's all going to be negative, right? But that's not what we're talking about. We have a positive number, right? I can have countless possibilities of what could happen, but right now what we're looking at, this just tells me that this cannot be negative at all. Okay, so now I have t to the power 8. That's the first factor. So since this term can never be 0, as I said, is always going to be bigger than 0, so ignore that term. If t to the power 8 is equals to 0, we know t must be equals to 0. That's one of the critical points that we have. The other critical point we have is going to be getting from this guy. If 9 minus t over 2 equals to 0, then t must be equals to 18. Okay? So we have all of these possibilities out there. So I know the critical points are going to be t equals to 0 and t equals to 18. And now I have to test what's happening around this interval. Okay, so I'm going to put 0 here. I'm going to put, 18 here. And then I can test the points before this point, in between this interval, and after this point. Okay, excuse the noises in the back. My dog's just kind of, all over the place. So we're having to pick a point here. Let's pick t equals to -1. Okay, and we'll pick t equals to 1. And we can pick t equals to, let's say, 19, okay? And evaluate the derivative at that point to just make sure that we're able to find out what's happening to the derivative, okay? So now this question has been asked from centuries and centuries that I've been tutoring. I don't know, people before that too. So if you are testing and finding out if the function is increasing, we're looking at the behavior of this guy, okay? So these points needs to be plugged into the derivative to be tested there. Okay. So we need to see what the derivative is doing, so just plug this point in the derivative. And from there we can figure out what's happening, right? So I can try to do a rough math here because I know this is the only term that's going to control my sign, right? Or essentially it'll just be, what I'm actually looking at. So if I plug in t equals to -1 there, this term will be 9 minus -1 to the 9 divided by 2. So this is always going to be a positive term. So the function is increasing in that interval. If you pick up t equals to 1, and then you do the math, what you're going to get here again is 9 minus 1/2, which will still be a positive number, so this is still increasing in that interval as well. And after 18, if you pick t equals to 19, then it might slide, okay? Then you would have to do this with calculator. 9 times 19 to the power of 8 minus 19 to the 9 divided by 2. I'm pretty sure this term is bigger than the previous ones, making the whole thing negative. Okay, so I know the function is increasing from the interval in this notation, and it's decreasing in that interval after that. So to just give the answer, the function is increasing from negative infinity all the way up to 0, and then union from 0 to 18. Remember how I didn't really write it's increasing from all the way from negative infinity to 18 in this case. The reason is because it is not increasing at 0. Okay, function is having a 0 derivative at 0, so we don't have to, include that point as an increasing point. So that's why doing this little funny math is just going to eliminate that. Okay. The sign between the brackets is a union. Okay. Now we're going to check some questions here. Let's see. So yeah, to find a max and a min is coming up next, okay? We'll talk about that in just a second. Don't worry about that. And to, on a test, you should check so this is exactly what you're going to get marks for, okay? On a test, you have to show your work, how you're checking these points to have a max and a min, and you have to literally pick in points and find those values in those intervals and get those answers, okay? That's very important, okay? And then why is it to the power of 9? Because the derivative has t to the power of 9. Okay, so that's this, and the union sign basically is going to tell you that you have to take the interval that's before this and also take the interval after this. So basically union is just combining those two intervals. Okay, that's increasing, and for the decreasing part, it's going to be decreasing from 18 onwards to positive infinity. So that's where it's decreasing. Okay, that's how we do this, right? So I made an hour-long video talking about how to do all these things, finding max, finding mins, inflection points, what to do and what not to do in already on my channel. Okay, so that video is already there. If you guys want to link that, I'll link it up here. So if you feel like you need to do more, learning of what's happening there, I would highly recommend checking that video out. Let me just pull the link and plug it in the chat. Yes. I know usually people don't pay attention to the videos until the very last moment, and trust me, everybody's same. So I sent you the link. Please click on the link, bookmark it if you need it for later, because I'm not gonna go into super details of what's going on with this thing right now. Okay, I want to show you a different approach on how to get these questions faster. Okay, and just want to clarify, the only thing I wanted to keep sure, you will see all these constant examples coming up back and forth again and again. Exponential functions can never be negative and can never be 0, because an exponential function from pre-calculus has a graph that looks like this. Okay, this graph will always stay positive and it will always stay above 0. It's the way it's defined. It will never be there. You cannot find a number, okay, because e is a number, right? You cannot find a number that e needs to be raised to in order to get a 0 here. It's just not possible. Okay. Yes, even e or any other exponentials that you probably have, let's say 2 to the power something, right? Can you find a number that you would raise 2 to the power of to get 0? Well, you can't. So we don't do that, right? So you said the first derivative and the second derivative, then plug the values to find increase in decrease. So see, there's a lot of questions happening here. I would really want you, if you have questions regarding the methodology and what's going on, it's highly recommended to check that video out, okay? Because it makes sure we talk about all the things in a systematic manner, one by one, and focused on one example. So we do all the things for one question, right? So that you have a flow of what's been asked and how you're going to do that, okay? What I'm going to do now is I'm going to tell you guys how to use tools that can help you do this on an exam much faster than what you're looking at, okay? So now, I have a question. I guess from what I know, you guys are allowed to use Desmos during an exam, right? Okay. So you have this, and yes, I do make for Calculus 2 as well videos, just making sure that you guys understand. So I'm going to go to Desmos here, and I'm going to try to show you how to do this math a little bit easier on a graphing calculator to see what's going on, right? So I'm going to go start from the scratch. I'm going to show you how to use it if you guys haven't done it before, and try to pay attention to this. This is very important, okay? And it can save you tons of time here. So the way you would use Desmos to kind of see the graph and find those values that you're looking at, we would first of all have to define the function we're working with. Okay, so in this case, I'm going to define the function f of x. So you just go here, literally type f of x equals to, the function that we were working with was 1/2 times e to the power of negative x divided by 2 times x to the power of 9. Okay, this is exactly the function that we were working with. Okay, it's not different from what's happening. Okay, so I'm gonna get to the topic of finding globals and endpoints. It's also covered in the video too. Okay, so make sure we're looking at globals and locals and how are these intervals going to be formed. All of that stuff is in the video. Okay, so go check it out if you need help with that. This is the function that we're looking at right now, and the graph, I can zoom out to show you what's happening to this graph. I'm pretty sure it should come down eventually, or yes, it does, but just doesn't happen to be in a very nice, manageable way. The values are very high, and this is how the function looks like, okay, on a scale. And now, if I was to ask you where this function is increasing, what you need to do is you have to observe the derivative of this function. Okay, and to observe the derivative using Desmos, all you have to do is type in f prime of x. So you see that? You just do the apostrophes and you have this kind of function here, right? So we have f prime of x visible here. If you are getting confused by seeing a couple of functions there, even though that the color is just going to help you out figuring, but if you're having trouble, you can shut off one of the graphs by just tapping on the color on the top left. So see, if I tap on, that little circle on the top left, it shuts off that particular graph. Well, to input f prime of x, you just literally have to, use the apostrophe s, the apostrophe sign, right? So f prime of x, very easy. If you're doing it on a computer, it's much faster. I'm doing it on my Desmos on my iPad, so it's a little bit tricky. Okay, so now we have the f prime. I can shut off the original function, but keep it there, so I can see the derivative graph in its whole glory. Okay, so now here I'm looking at it, and I know to find the critical points, all I have to figure out is where this function is crossing, the value 0. So I can tap on this function and it kind of marks some points in the gray. The first point in the gray is 0, 0, where you have it here. And then the next one is right here at 18, and that's exactly what we found out. There are going to be no critical points after this because you don't see any crossing happening, and Desmos doesn't show you that. Okay, and I'm getting to the second derivative. Just be patient with me, okay? You got to bear with me for someone. I want to make sure everybody's explained out with all this thing, right? So you get the y and x axis to change with the scale. If you're using a computer, okay, this would be a little tricky for you to do that. So if you're using a computer, it doesn't really scale axis manually. Right now my y-axis scaled, but my x is okay. To do that on a computer, I would like you to go to the top right and click on the setting here, the little wrench, and then you can pick the x values and the y values where you want to be, and you can also pick the the lower bounds, the upper bounds, and fill in this. So you can pick like any random numbers, like 0, 100, whatever you want to do, to make sure you can fit the graph there. This particular example probably is not the best example to show because it's like very weirdly scaled. So go to the top right on the wrench, you click on it, and then you would have all the options in Desmos that you want to change, okay? So if you want to see the x-axis starting from -20 up to 60, that's what I have on my picture. And then we have on the y-axis, we start on the bottom at -4 and go up all the way to 7.5 billion or something like that, right? So you can type that in unless you see that graph fit in your picture, right? Yeah, so now you have all these graphs and the critical points given like this, right? Very easy. Now I'm going to come up to the next thing. The next thing we would usually do is to figure out what's the sign of the derivative in the intervals, right? So now I have these intervals where it's going to be -infinity to 0, 0 to 18, and then 18 to infinity. Same intervals like we got before, right? Now, there are two ways to figure out the sign of the derivative in those intervals. Remember we used to pick a point and evaluate using calculators? You can do that in Desmos, okay? To pick a point before that and evaluate it, all you got to do is just do f prime, and now plug in the point you want to evaluate, okay? So let's say if I'm checking the interval from -infinity to 0, I would pick a point -1. And the moment I do that, I get a number. It's positive 7.83. So I know the function is basically having a positive derivative in that area or at that point, right? So if you find critical points like this, can we just write those? No. They want you to show the work. So Desmos is going to help you second check your work, okay? And make calculations, computations, and all those things faster. That's the only thing it will do, okay? It will not substitute the actual work you have to do on the exam. Okay, this is a tool to help you, not a tool to bypass the exam, right? So make sure we use that, right? So we picked the point f x equals to -1 and evaluated the derivative, and then we did it. So just want to quickly clarify that critical points are the points where the derivative function crosses 0. Okay, so if you have the derivative function plotted like I have it in the blue, you click on it, you will have 2 points. It crosses 0 there, and it crosses 0 here at 18. Okay, so that's how we know that. But you would have to do that manually, doing the derivative, setting it equals 0, finding those points. This is just there to help you check those. I did that work here. Okay, I manually find those points t equals 0 and t equals to 18 here, but the Desmos also helps me figure out that I'm actually right, so I don't have to keep on second guessing myself. Okay, so that's good. Okay, on the exam you would have to do this. You can't really use just Desmos to find those critical points out of blues. So you have to do the work. Desmos is there to help you, right? And now at this particular point I'm talking about how these calculations could be done using Desmos, okay, to help you fast, get the process done faster. So here I pick t equals to -1 and I have to manually plug it into the calculator, do the finicky work to get that value. But Desmos can help you figure that out faster. All you gotta do is just plug f prime of -1 there, right? Similarly, if you want to find the value of the derivative at the other point that we picked up here t equals to 1, right? So if I want to use Desmos to find that value, what I'm going to do is I'm just going to go there, plug f prime of 1. And that tells me the value is 2.5577, whatever. And that is also positive. So we know the derivative is positive at those both points. And the point after 18 that I picked was 19, right? So I can pick that value now. And I get negative 317,000 whatever number, right? And then you'll know that of course the derivative at the value 19 is extremely negative. Okay, so think about the question you're asking. What would happen if you put 0? Well, what is 0? And why are you putting it? Ask that question to yourself. Are you just curious what's going to happen? Then it's fine, okay? The reason why you should not put 0 here, because 0 itself is a critical point. And being a critical point, 0 ensures that the derivative is 0 at that point, right? So even if you plug in 0, if you want to be curious, you can do that. You can try to plug in the value of f prime of 0, let's say. Well, I know it's going to be 0, because that's basically the critical point. So the slope is defined to be 0, okay? So if the slope is positive on both the sides, the critical point, what does it mean? Very good question. This is a question that I would really like to answer, okay? Well, what kind of context are you asking for? Does it strip off, from 0 to be a critical point? No. 0 will still be a critical point. In this case, the slope before and after 0 are still positive. That means this function, this point of this function cannot be tested by first derivative test. So we can't really tell anything about its maxima or minima nature, but it's still a critical point, okay? So to tell more about is this a minimum or a maximum, you would have to use the second derivative test. Okay? That's all it does, and nothing special. If you look at 18, right? If that's the critical point, you see the slope before 18 was positive and slope after 18 is negative, then you know 18 is going to be a max. And you can indeed see that happening when I turn the function graph on. You can see that there's a peak at 18, right? That's what we're looking at. So that makes sense. However, the 0 is just not, really a max or a min in this context when we're looking at it. It's just a point where the derivative momentarily becomes 0, which makes it a critical point. Nice, but it doesn't really give it any title to be a max or a min. Right? Can you tell the min and the max from f of x? Yes, you can. Of course, in this case, the only max is here, and there's not really any mins. if you're looking at it unconstrained at this point, because this function goes deep down in the hells of negative infinity, and it doesn't really, have an end towards its minimum. However, the maximum is easily found out. So that's easy, right? And about a saddle point, more about that in the video. So check it out in that link. You'll be able to figure out exactly what we call a saddle point. Right now, I don't want to mix up context, okay? I'm focusing on how to tell you guys to use Desmos here, okay? So that's what we can do using the first derivative analysis. Easy peasy, right? Now if I want to move on to the next step and find inflection points, then you know that we need to have the second derivative in hand, right? So second derivative is also easy. I'm going to delete all these values because I don't need them. I'm going to try Desmos to help me plot the second derivative, and that's going to be done by just doing f double prime. So you have two apostrophes now and an x. So I'm going to shut off. I'm going to make this a first different color with let's say orange, and I'm going to shut off the derivative so we don't get confused. Okay, so this is now the graph of the second derivative that we see here. Not bad, right? It looks okay to me. And to find the inflection points for this function, what would you have to do is you have to find where does this function cross 0, right? Because inflection points are the points where the second derivative, will be 0. It is not entirely true that you only need the second derivative to be 0 for a point to be an inflection point. The point also has to do some inflection. That means the sign of the second derivative must change as well. Okay? If you want to know more about that, I do talk about that in the video as well. So that video is very important. I keep on, pointing back over there, but it's going to save a lot of trouble and clarify a lot of things. Okay? So here, I'm going to look at the inflection points, which are the possible inflection points here. And those points are right here. It crosses 0 at 0. The next place it crosses 0 is at 12. And the next place it crosses 0 is at 24. So I have all these points labeled out here. Now, excuse me, I want to check whether the inflection actually happens at these 3 points or not. So now I have, I'm going to put that on the notes as well. I don't know why my throat's hurting too much today. Sorry about that. So I have these points here, 0, 12, 24. Okay? And I want to test like points in between these intervals and see what's happening, right? So I'm going to pick a point in this interval. So I'll pick x equals to -1 in that interval. I'm going to pick x equals to 1 in that interval. I'm going to pick x equals to 13 in that interval. I'm going to pick x equals to 25 in that interval, right? I'm picking these points, and I'm going to test the second derivative at all these points to know what's happening and how the concavity is doing at that point. For this purpose, I will use Desmos, okay? Instead of plugging this thing and finding the second derivative and doing all the things, yes, you can pick any number in those intervals, okay? I'm just picking the ones that just, came to my mind. So it doesn't really matter, okay? So now I'm going to use Desmos to find the value of second derivative at -1. I'm going to find the second derivative at 1, second derivative at 13, and second derivative at 25, okay? And you see how fast it is in Desmos, okay? It's going to just have f double prime of -1. So I get -66.9. So I know this is less than 0. So the function is concaving down in this interval. Okay, that's how I know this. Moving on, if I go back to Desmos now, I'm going to go and tell you a faster way. Instead of typing it all the way in the exam, you can do this way, okay? So watch closely. If you look, there's a gear sign in the top of the comments pane right here. If you go back here, I'll show you again. I'm in this pane that I just opened on the left. You see there is a gear sign on the top here as well. Okay, right where the done is now. Okay, so you click on the gear option, and that will open up all these things for you. All I want you to do is hit this number, the copy button here. Copy, copy, copy. Okay. So when you're picking up a number and copy them, so you do that, you get this. See, it makes multiple copies of it. So now all you have to do is just change these numbers. So we were testing, the next point we were testing was f equals to f prime of 1. The point after that was f prime of 13. And then it was f double prime of 25. So now I have all these values here. I know f double prime of 1 was 19.8, so it's positive, so it's concaving up. F double prime of 13 was a large negative number, right? It's just a large negative number, so it's going to be concaving down in that interval. It's going to go here, less than this, concaving down. And f double prime of 25 is a large positive number right here, as we see in Desmos, 36,961. So then I just move this here. I know it's positive, concaving up. So now this helps you figure out the computations easily, right? Because on the exam, they don't expect you to, show your work for how you computed this. All they want you to do is plug it into the second derivative and spit out an answer. So I think Desmos helps you save a lot of time when you're doing those computations. It does it much faster as compared to a manual calculator, right? So first derivative finds critical points and second derivative find inflection point. Absolutely right information, and that's exactly what you're going to find in that video that I made, okay? So I talk about all the layers of what's happening in that calculus tools video. So please check it out. I really recommend it. Okay. So that's how Desmos is going to help save us a lot of time on an exam, right? So now what I want you guys to do is look at a problem that I made. So I'm going to show this right now because I have came up with some questions which I feel are very important for this particular exam, and I'm going to send this document to you guys too, so don't worry about it, okay? I'm going to post it in both the Discord and the Facebook group chat. These are basically 6 questions which I feel you guys should be paying more attention towards, okay? The first one being is just the same kind of idea what we did. So we're looking to determine the following for the given function. We have exponential of negative 2x times x cubed, and we're limiting this domain from -1 all the way to 4. Okay, I want to show this example in Desmos. Yes, the solutions for this is also made. I can always send those as well. I'll post both the questions and the solutions. Okay, these are definitely the plausible long answers. That's what I'm like focusing on. And yes, -1 and 4 are the exterior edges. Okay, so now I want to go to Desmos and show you how you type this function and only see this function for those x values, like in a restricted view. Okay, so let's go to Desmos and show this idea over there. I'm going to put the function up there. I'm going to get rid of all this information. Okay, and then I'm going to type in my function first. F of x is just going to be e to the power of -2x times x cubed. So like in this case, you see most of you guys are gonna get stuck in this. I'll talk about hill climbing in just a second, so don't worry about that. That's very easy. So like in this case, most of the times when you're working with like different graphs, you are on different scales, and this graph just looks like a flat L in this particular view, and you can't really see it, right? So to make sure you return back to like the default view for this graph, you got to check out there's a right hand side home button on the screen, right? You see that? There's the home on the right side of the screen. You tap on that and it just automatically brings you to the scale where the graph is visible. Okay, of course it's not that easy to see, but that's the graph of f of x. Okay, but we have to only see this graph for the x values from -1 to +4, right? So how we do that, I'm going to go to this next tab and I'm going to input a restricted view of this function. And the way you do that is you're going to start with the squiggly brackets. Okay, you can find them on your keyboard or you can find them in Desmos and the keyboard, the full keyboard. So you'll have the squiggly brackets, and now you got to give them the restriction that you're looking at. The restriction here is -1 less than equals to x less than equals to 4. So that's the restriction that I'm looking at, right? After I'm done putting the restriction, I have to put a semicolon and then have to define the function from there. So it'll be just semicolon f of x. Okay, so this way I can only see the piece that I'm interested in. So I'm going to shut off this, and that's my graph. So this graph is now only visible for the things that I'm looking at. Okay, just the function from -1 all the way to 4. So by looking at the graph, can somebody tell me, I'm going to try to make it like this so you guys can see everything, right? And now this Desmos can do a lot of things, of course. I want to tell you what you can do. So this is the restricted view. Can you guys tell me the global minimum of this graph? The global minimum. Or tell me where that global minimum occurs. You know the global minimum is all the way down here, right? Like at this point, right? So the global minimum is happening at -1, and the value of the global minimum is -7.389. Nice. So that's good. Can anybody tell me what the global maximum is? Yes. The global maximum is right here at 1.5, and the global maximum value is going to be 0.168. Does everybody agree with me on that? Right? Nice and easy. So now we're going to see what's happening here. What do you want me to repeat? You want to see where the global minimum is? The global minimum is all the way in the bottom here on the graph, -1, 7.389. And the max is all the peak of the graph, right? The max is on the peak of the graph. So you tap on it, it will give you the value. What's happening in there. So Desmos, so try to play around with it, you'll see what's happening. The question is, how do we know when to state the max value, the y value or x value, the maximum? So think about it. The critical point is just the x value. So in this case, if I ask you what's the critical point where the maximum is, you would say 1.5, just the x value. But if I ask you explicitly what the maximum value is, then you would have to state the y value there, which is 0.168 in this case. Okay, that's how we have a distinction between them. Nice and easy, good. So now we have our function. I have to tell them where this function is increasing, decreasing, and what's going on, right? So that was the question in the problem. They want you to find the intervals of increase, intervals of decrease, and critical points. So let's do that. Using Desmos and not doing any physical work. Of course, physical work is for you to practice. I will post the solutions to that as well. But I just want to show you how Desmos can single-handedly solve this problem without any work. Okay? So now I'm going to be having another one. Going to the gears here, making a copy of this function. Okay? And replacing this f with an f prime. That will just tell me the derivative in that zone. So I'm going to change this to a color of red. Shut the original function off, and this is my derivative graph. Okay, of course, you don't have to like go all the way onto those things. We have to see where this graph is going to have crossing of zeros, right? So this is the first derivative plotted here, only in the restricted zone, and then we see there's a zero crossing happening at 0. So 0 is a critical point, and there is a crossing happening at 1.5, which is also a critical point. So now we have to see and evaluate these on those intervals, right? To check what's happening. So I can figure it out. I can just scribble on this. I'll put a number line here. I know 0, 1.5. And I can pick a point in this interval. Pick a point. I can't really draw these brackets nicely here. Pick 3 points in this interval, right? I can pick -1 here. I can pick 1 here. I can pick 2 here, right? Whatever. And I want to check the sign of this of the first derivative from there. I can go to Desmos again. Just plug those numbers in. So f prime of 1, or basically -1, my bad, is positive 36.94. So I know function is, derivative is positive in this case, so it's increasing. In between 0 and 1.5, I'm going to pick 1, so I can change this, or I can type it again. I can have all this information here of 1. So in 1, it's 0.133, or 0.1353, right? Yes. So it's still positive here. Okay. And then we have 1.5. After that, we pick 0.2, so I'm going to do that, evaluate the derivative at 2. So it's negative 0.07, so it's negative here, so I know it's going to be decreasing. So if they ask you for the intervals of increase, you know the answer is from -1 all the way to 0 first, and then union from 0 to 1.5. Does everybody agree with the answer here? Does everybody see how intervals of increase are -1 to 0? And of course, please keep an eye out. It's a closed bracket at -1. Okay, usually we don't do that. For infinities, we have open bracket, because we're working with a closed interval here, so I will use the closed brackets for the points that could be included inside a domain, right? That was a little catch, and I want you guys to pay attention to that. Okay, so the function is increasing in that interval. The intervals of decrease here are basically going to be from 1.5 all the way up to 4, and including 4, because 4 is the other endpoint of the analysis and it's included in the thing. And the critical points, of course, as we found out, are going to be x equals to 0 and x equals to 1.5. How does everybody feel about doing this problem in Desmos? Do you see the utility that I want to show you guys? Right? It's so much easier to do that way. So, of course, you have to do the physical work to get those numbers out, but if you are lacking on time and but like you're getting stuck in all those things, I want to make sure that you guys are always have this handy on the same side. I know it will be very difficult to have time to check back to your solutions, so that's why I like you guys to work on Desmos alongside for all the problems that you're doing physically, so that you always have like a calculated version of that open on your computer or any device that you're using, which you can refer back and check whether everything that you're doing is making sense or not, right? That's the only utility I can do here. Yes, the recording will be uploaded after I'm done finishing this setup. I'll just upload this and just get it on there, right? So the reason why I'm not doing more hands-on work is because the calculus tool video covers all of this particular in a lot of hands-on work, okay? So there is an example that I work it out. Plus, these questions I specifically prepared for you to gauge yourself, okay? So I don't want to really work on these problems with you at the moment. I will be there all the time to help you out. My solutions will be well in detail so you can follow along the work. But I want to make sure you guys have a chance to do this, right? These questions will be posted after the session that we do on both Discord and the Facebook group chat. Okay, so you'll be able to find them. Don't worry about it. Okay, I'll also post these links in the description of the YouTube upload that I do for this recording. So you'll have all of them after we're finished. The thing that I want to show you like right now at this point is the utility and how you should use and optimize your time. That's the whole point. Okay, so that was the maxima minima. Now I want to talk about optimization, okay? And move on from there to our ideas. I'll just quickly open up this page, right? So can you please go over B part for this one? You mean I'm talking about the, you mean B part of this, the local global extremums for these? I already did that on Desmos, right? Didn't we? If you look at this function, okay, right now, the global maximum is at 1.5, and the global maximum value is 0.168. The global minimum is at x equals to -1, and the global minimum value is -7.389. Right? That's the global max and the global min. And now if you talk about the local min, you can say this happens to be a local min, because at 0 you'll see this function is like steadily stopping at that point. So from comparing these values on the endpoints, of course, in the calculus tools video I talk about how to test and which points to test and how to classify them as globals and locals. So that video will definitely help you figure out what's happening. Okay, I don't want to like waste time because there's so much more to cover right now. I want to go over some optimization word problems. And especially people have trouble with biological context. I want to show how we can do these problems, and just move on with that first. Okay, so check that video out. If you have any questions, you know how to reach out to me. I'll be more than happy to help you. Okay, so let's move on and save everybody some time, and move on to this example. Right. So optimization. When it comes to optimization, what I personally feel is that your prof has not covered enough problems on optimization. The only things I saw were basically on OQ, and there's one question about the IQ, right? And then making sure that we just had just a little piece of information given in the study guide, where just one question was there to just optimize the area for an ellipse. So those kind of problems are very easy and are not too difficult. What I would like to do is work on this problem with you guys, okay? Let me try to pull up this problem super quick. I don't know why I have so many tabs open. It's gonna go back here. Let me pull that problem out, okay? Just give me a second. Well, you can't have an area problem, right? You know, you got to make sure that we understand what's going on with the area problem too. It's very easy, as long as we can have like a way of going about these problems. That's all what we have to focus on, right? So I'm gonna go back and let me just quickly find that question. Should be somewhere here, and then we can, you know, once we have an example to work on, we can both just kind of see what's happening here. Okay, so let's focus on this. I'm gonna write this problem out with you. I want to work on this, and I have enough problems in the sheet that I work on with you is also on it. Yeah, problem with the soda can. A lot of those things are there, right? So I want to make sure that we do a similar problem here so that we don't miss out on it, okay? Awesome. So we're looking to make a closed rectangular container. I'm gonna put this out here. So we're trying to make a closed rectangular container, okay, and this container needs to be with a square base. So you guys know how a square base container would look like. It will be just a square in the base, and it will be a longer or shorter, you know, on the sides to feel that. So it's supposed to be made from two different materials, okay? We have two different materials. And now we're particularly looking at the material for the base, okay? Material for the base is gonna cost you $5 per centimeter square, okay? Or like I would say per meter square, because it will make the problem easier, okay? So you have $5 per meter square for the cost of the material of the base, while the sides, okay, material will just cost a fraction of it. It will be $1 per meter square. Okay, it's very cheaper to make the sides than to make the base. It's a very optimal problem. Sometimes the box's base needs to be very heavy, right? That's what we have. So now we're gonna find the dimensions. Find the dimensions of the box or the container, okay, which has the largest possible volume. So we have the largest possible volume. This is not an area problem, this is an optimization problem, okay? And what we're trying to optimize is the largest volume possible in a given fixed budget of $72. So square base. It has a square base. I'm going to repeat the problem again once I put it out. You know, we're looking to make a closed rectangular container. So it will have a lid. Okay, that's what the closed tells you. And it has to have a square base. And we have to have two different materials to construct that box. The material to construct the base is going to cost $5 per meter square. Material to construct the sides is going to cost $1 per meter square. And we want to find the container which has the largest volume in a fixed budget of $72. So we can't really spend too much money on it. Right? Does everybody understand the question? Is there anything that you feel that's not clear in the question? Pretty easy, right? If you think about it. Nice. So now we're going to start solving this problem, right? To start solving this problem, we have to first of all lay out two things, okay? What is my objective? And what is my constraint? Okay, what do you think, guys, is the objective here? Yes, how much? So we have to find out how much material to use only to spend $72. Well, that could be any sort of material, but we want to find the material in order to have the maximum volume. Okay, so objective is to maximize volume. Okay, that's the thing. And the constraint is the budget. We can't really, go above the cost of actually that we're allotted to work with, right? So we're in this whole realm. So now we have to start making these objective figures to figure out what's happening. Okay, so I'm gonna go to the next page and try to draw out what's happening. So I'm gonna lay this block in this box like particularly flat to see what's happening. If I see all the pieces of the box, this is gonna be the base of the box. Okay. You can say this is one of the sides. Wow. I don't know what this app is doing for me, but it's okay. My drawings are not helping us today, but trying my best, guys. So that's the box with its sides. Okay, so what I'll do is I'll try to share the question with you guys. Let me do that so we don't lose a track of it, okay? Just give me a second. So I will be I just, gonna paste it here, just try to see if that works. Can't really do that. Okay, so I'm gonna try to save and send it in the chat, okay? So you guys can open this up with your end. Hold up, please, just 1 second. And there we go. So the chat should have the question there. So you guys can click on it, you can save it if you want, and then we're gonna be working on it, right? So that's the box with its all sides, where you have it flat, and they're always gonna be, the top of the box as well. Okay, which will be a square. Does everybody see this picture that I made? And does it make sense to everybody? Like, this is the deconstruction of a box. Okay? So now we know the base is square, so the top has to be square as well, otherwise it won't be a closed box, right? Very common sense. Nice. So let's try to label some quantities here, okay? So I'm gonna call this side S, so that would make this side also S, right? And that would make this side as S and that side as S as well. Make sense? Nothing crazy, right? That's for the base and the top, right? That's the first variable. And I'm gonna call this side H, because that will be basically the height of the box. So all of these dimensions are gonna be H, H, and H, and all the way H, right? Okay, it's turning out to be very obnoxiously loud today, but hope you guys don't mind. Okay, so everybody see how I labeled out all these heights as well, right? So I introduced two variables here, S and H, and now I have to look back at what expressions I can make for my objective and my constraint. Okay, this box will have a volume, I'm going to call this V, equals to S times H. Does everybody see that? The volume of the box is going to be S times H. Right? Not too bad. And then my constraint here will be the area, and the cost of all of this total, okay, would be equals to $72. That's my constraint, right? So let's first of all find the area of the sides and then the area of the base, okay? So area of the base will be S squared. Does everybody agree with me on that? Awesome. Area of the top will also be S squared. Right? Nice. And the area of one side will be H times S. Right? So we have one base, one top, and four sides. So the area will be S squared for the top, or for the base. Okay, and the area for the sides is going to be how much? It's going to be the top, which is S squared, plus 4 times HS. Okay, so this is basically the sides, and this is basically the base. Does everybody see how I have this distinction of what I'm using in what area I'm using in which dimensions, right? Do you guys see that? The sides are going to be this much, and the base is going to be S squared. Awesome. These are the areas. Now we have to have the respective costs. Okay? To make the base, it's going to cost me $5 per centimeter square. So for S squared centimeters, I need to have it as $5 multiplied by the S squared. So it's going to cost me $5 times the whatever the area of the base is, right? Yeah, the other S squared is the top, but I'm going to, consider that as a part of the side because it's going to be made from other material. Okay, that's why I made that other material in pink color. Okay. The top is going to be made by the same materials that's going to be made for the sides. Yeah, sides are in the bracket with the top because that's going to be made by a different material. Okay, the only base is going to be made by expensive material. So that's why the area of the base times 5 is going to give us this. And then all of this is going to be made into $1. You see now why I had this pink associated with the dollar. Purple is the expensive material. Pink is the cheap material. We only know the top is going to be made as the same material of the sides. That's why top is combined with the sides in this particular case. And the base S squared is in purple because it's $5 to make that thing. Does it make sense? Is everybody with me? I know this will take a little bit of time. If you have any questions, please ask me. The other pink square is for the top because it's a closed box, right? So the purple square is the base and the pink square is the top of the base. How is the S squared in the sides? Well, this should be sides plus top. My bad, The objective that I was telling you this is going to be sides plus top because those things are going to be made by a $1 material. Okay, that's why we have it there. So this total cost that I'm going to be having it, $1 from the actual question. The actual question is telling us the side materials are going to cost you $1 per meter square. And the base is going to cost you, $5 per meter square. So that's where I'm getting all that information from, right? Good. So now this, whatever budget I'm going to be spending on this, must be equals to 72 because that's my constraint, isn't it? That money needs to be $72, or else it won't make any sense, right? So now I have all the pictures here, things here, and I'm going to move on and do some math on the next page, okay? So I'm going to copy this information over to the next page, so don't worry about it. My objective is volume equals to S squared times H. Okay, my constraint is that $72 must be equals to 5 times s squared plus s squared plus 4hs times 1. So it's only just going to be this. Yes, so now I'm going to get to that step where I have to like use the constraint to isolate for one value. Okay, and then move on from there. So this is what we're getting here. Okay, that's my constraint. So now the next step that follows after this is use the constraint to isolate. In this case, I would say, for h, and substitute in the volume. Yes, you guys did learn how to do this. If you are not liking on this, I would seriously be worried about you, just to be honest. But this is exactly what you have to do. There is a very high chance of this kind of problem to show up on your exam. Okay, so please, let's keep on moving. So here I get 72 5s squared like this. So I can resolve this a little bit. It'll be 72 equals to 6s squared plus hs. Okay. And if I isolate for h from there, what I'm going to get is 72 minus 6s squared equals to hs. And h is just going to be 72 minus 6s squared divided by s. Does everybody see how I isolated for h? Which 4? Oh, yes, my bad. I'm blind. Thanks for pointing that out. So it will be 4s in the bottom. Yes. Thanks for pointing that out. Right? So we got that. This is my h value. So now my volume expression will only be in terms of s after I substitute. So it will be s squared times 72 minus 6s squared divided by 4s, which you can simplify by canceling one of this s out and foiling that inside. So it'll be 72s minus 6s cubed divided by 4. Does everybody see this is going to be my function for volume? Any questions regarding this function for volume? Everybody's okay with that? What is to the power of 4? Oh, I'm just canceling this. This was power to the 2, and it got cancelled with one of the s in the bottom. Okay, this s, just cancel that 2 over there to make it s, right? So the thing how we're going to do this, I know the volume is going to be s squared h, so my purpose is to find what h is equals to in terms of s from the constraint and plug it in there. Okay, so I use the constraint here to simplify for this and isolate for h. Are you clear with that part? Finding the h. Right? So finding the h is okay. And now all I did is just took this h and multiplied here in the place of h here. So when I do that, I get 72 minus 6s squared divided by 4s. And then I just resolve this expression to get my vs value. Right? Is that clear now? Okay, makes sense. Good. So now we're at this function, and now we have to do our math to find where this function is going to have a maximum. So this is my constraint function here, and I can just optimize this. I multiply by s squared. I didn't add s squared in it, right? I multiply the function of h because s squared times h, I just substitute for h. It's very simple. This h value just goes there, right? Good. So now I'm going to move on, and I'm just going to have this function here, v of s, written as 72 s minus 6s cubed divided by 4. Okay, and I'm going to start by taking its derivative, finding the critical point, testing the critical point, and then concluding my results. That's what my aim is going to be. Okay, so I'm going to write this in this format. It's not different, it's just a different way of writing it. Okay, Does everybody see they're not any different from what I just wrote? I just expanded it out so that I can work in peace with numbers. Any questions regarding this? Everybody's good, right? Now I'm going to start to take the derivative of this function, which I'm going to get as 72 over 4 and minus 18 over 4s squared. That's my derivative. Very easy. Set it equals to 0 to find the critical point. I would get 72 over 4 minus 18 over 4 s squared equals to 0. That tells me 72 over 4 equals to 18 over 4 s squared. That tells me s squared must be equals to 72 by 18. And I guess they're divisible. Yes, they're both divisible by 9. This is 2, and 72 divided by 9 should be 8. Right, and that's just basically 4. Right? Okay, so we have it in that perspective. So we have it as 4. That's nice. So s squared must be equals to 4. So s could be equals to plus or minus square root of 4, which is going to be plus or minus 2. We're only going to consider positive 2 because s is a dimension. So it can't be a negative number. Right? So that's what we get here. That our s needs to be 2, which is nice. Nice and easy. So now we have to actually ensure that we're going to get a maximum volume at this point, right? So we have to check this by either first derivative or the second derivative, right? So we will find the largest volume. We'll go back to the question and revisit it. First, we have to test this point, that this s equals to 2 will really give me the maximum volume or not. Okay? So you can check by first derivative or you can check by second derivative. I'm going to do them both right now to make sure you guys understand. Okay? So I'm going to move on the second page. I'll show you how it's done by the first derivative as well. Okay? So my function here, v of s, was 72s minus 6s cubed divided by 4. And my v prime that I found out was 72 over 4 minus 18 over 4 s squared. That's my first derivative here from what we've done before. The critical point that I'm testing is s equals to 2. Okay? So what I do is I put this point on the number line 2. I pick a point before that. Let's say pick x equals to 0. Or in this case, s equals to 0. And find the derivative at that value. When you plug in s equals to 0, you get 72 divided by 4. Which is positive, hence you know the function is increasing. Okay? Before that. Good. After that, I pick a point. Let's say pick x equals to, or s equals to 3 in this case. My v prime of 3 would mean that I'm having 72 over 4 minus 18 times 3 squared, which is 9. So that will just be like a very big number. 18 times 9 divided by 4, which I am pretty sure is going to be negative. Right? So we have it in this point where you're looking at this being a negative number, so we know this is going to be decreasing in this thing. So the way you conclude this by first derivative test is by saying that the v of s is increasing for s values smaller than 2 and decreasing for s values that are bigger than 2, then you know s is a max. You see how I conclude that example? So at this critical point, the function was increasing before that, and right after that it started decreasing, so you know you're going to hit a max. And yes, you can of course use the second derivative test, but you cannot use second derivative test to see if a function is increasing or decreasing. Increasing, decreasing is only associated with the first derivative. Second derivative has nothing to do with increasing, decreasing. It has only things to do with concavity. Concaving up or concaving down. Okay? So we have that. That's the first derivative test. Is this clear with everybody? how we use the first derivative test to verify a result. This is very important. You will have to verify any critical point for max or min on your exam. You will lose marks if you don't verify it, okay? This is the first derivative verification. Yes, please ask your questions. I would like to help you. So, what are you confused on? Are you confused on the test itself or what I did? Or, yeah, absolutely correct. If it goes from increasing to decreasing, yes, it's a max. Because if the function was increasing and then it starts to decreasing, you know that value has to be a max. It's just, it makes sense because the function was increasing towards some value and now it starts decreasing, so it has already achieved its maximum, right? And if you were to find a minimum, you would say if the function was decreasing before and then started increasing, it will have a minimum. So it's just like vice versa, right? So right now it's a local max or global max. We'll get to that in just a second. Right now it's a max, okay? So we'll keep that handy, and I'll tell you why it's the global max in just a moment. But let's go and do the second derivative test as well, just to make sure we have it here. You only have to show them one test, either first or the second. You don't have to show them both. But I'm going to show you both just in case, make sure everybody's comfortable with their own things, okay? So now moving on, I'll just do second derivative test to prove it. I'll copy down the information that I already had, which is 72s minus 6x s cubed 4. I knew my derivative was 72 divided by 4 minus 18 over 4 times s squared. And now to do the second derivative test, what you'll do is you'll find the second derivative. The second derivative from this function, okay, will just be negative 18 over 4 times 2s, which is negative 18 over 2 times s, which is essentially negative 9s. Okay? Any questions regarding the second derivative? Very easy and standard to find, right? Does everybody see that? Good, right? Now the way second derivative test works is you need to check what's happening to the concavity of the function at the critical point, okay? So the critical point we're testing is s equals to 2. So let's check what the function is doing at 2 from its second derivative. The second derivative of the function at 2 is telling you it will be negative 18, okay? So we can say the function is concaving down at s equals to 2, right? So the function is concaving down at s equals to 2. That means the function would have this kind of shape. And a function has that kind of shape, and then the critical point in that shape will be a maximum. Okay? If a function is concaving down at a critical point, the critical point is the maximum. If a function is concaving up on the critical point, it's a minimum. So that's how we do it. Just going to read through what we're looking at. So we literally take our critical points, put them on a number line, and then evaluate number before and after each critical point to see if it's increasing or decreasing. That's exactly correct. Okay? Or you can put them in the second derivative, check if the second derivative tells you the function is concaving up or down, and then conclude a result from there. Okay? If a function is concaving down at a critical point, the critical point is going to be a maximum. If a function is concaving up at a critical point, the critical point will be a minimum. All of this is covered in the calculus tools video as well. Okay? So this is how we have tested that the value s equals to 2 is indeed going to give you a maximum. Now we have to go back. I have to go back and ask and look back at what the question is asking us for. So if I scroll back all the way, the questions in original idea that they were asking us was to find the dimensions of the container. So we have to give them the dimensions. Okay, we know the dimensions that we have to give them are going to be the s value and the h value, right? Because those are literally the two dimensions of the container. We've already found out the s value, right? The critical s value must be 2 meters. Okay, we found that out. Now we have to give them the h value corresponding to this s value, right? So you go back here, and you remember we isolated h in terms of s right here, right? So h in terms of s is 72 minus 6s squared divided by 4s. So to give them the container's dimensions, s must be 2. So h must be 72 minus 6 times 2 squared divided by 4 times 2, which is going to be 72 minus 24 divided by 8. And I don't think my brain can do the work right now without a calculator. And just get this, you know, I'm going to run this with a calculator, just get the numbers. 72 minus 24 must be 72 minus 24 is 48. Nice. So 48 divided by 8 is just going to be 8. Okay? 6. Is it 6? Yes, 6. My bad. You guys are right. Where did the 2 come from? Well, we spent our lives looking for that 2 value, didn't we? We found the critical point as to be the 2 value. Right? And then this was a critical point. We tested that this critical point does it, right? I know it's easy to lose the track. I was just kidding. It does, because when you're solving these problems, it's easy to go follow the loop. Happens with me all the time. Okay? So thanks for asking that. You helped a lot of other people too. But 2 was a critical value that we found out. And now we're just giving them the dimensions because they were asking us for the dimensions. Okay, so that was this. I'm going to tell you how negative 18 represents the maximum. Just give me a second. I'm going to finish out the problem. S equals to 2 is the dimension for the base, and the height must be 6. So the box should be 6 times 6 times, 6 times 2 times 2. Yes. And it is, trust me, it is easy to lose track. So make sure you're following like the whole thing. I don't know why you're being kicked out. I'm sorry, I don't know what's going on. I'm not even touching the participant tabs, right? Yes, I know. If the prof did not go over this enough, I'm pretty sure this might be on the exam. That's why, you know, I'm leaning towards it. That's why I have questions on the thing there too, right? So now, to prove that it's going to be a maximum when this is negative 18, well, double prime of v being negative 18 tells you the function is concaving down. Okay? And the function when it's concaving down and has a critical point on there, that critical point has to be maximum because of the shape that I just drew there, right? Does it make sense? That's easy, right? Good. So that's what you need to know about this. And trust me, there's so much more to optimization than hill climbing algorithm. The hill climbing algorithm only works when you're trying to find maximum minimas from database graphs, not from functions. Okay, so we have to learn this. Your OQ was based on this. You were learning how to maximize volumes, maximizing areas, minimizing cost. There are a lot of problems, okay? So I just don't want you guys to get off guard on the exam, right? That's where I want to go. So that wraps up optimization. I did one problem with you. There's going to be a couple problems here on the worksheet. So this problem 2 is an optimization problem. Yes, s equals to 2 and h equals 6 is the final answer that you have to give them. Okay, because that's what they were asking you for. So in this problem, like I said, in this particular set question 2 is asking for, you know, population density and concentration of nutrients, and they want you to find the optimal nutrient concentration and find out the population density, you know, at that concentration. So you know you will be able to absorb this context. I want you guys to attempt this problem yourself. So problem 2 is an optimization problem. 3, 4 are differential equations. Problem 5 is also an optimization problem. Problem 6 is also an optimization problem. Right? I want to make sure that you do enough optimizations because I want everybody to nail the optimization problem coming on the exam. Okay? I'm pretty sure it's going to be either one of these or the ones that you saw in your tutorials. Okay? So I want to make sure that I cover all of those things. I don't want anybody to lose marks on a word problem. Okay? So give them a shot. I have solutions to them. I'll post them up. So I'll tell you what hill climbing is. It's very easy. I'll show you. Hill climbing is a piece of cake. Let's say you have a function here. Okay? By tutorials, I mean the study guides and the IQs and the OQs and all that stuff. Okay? So all those things, I just call them tutorials, and just to make sure we're covering up all of them. So let's say you have this function. The hill climbing algorithm works is you would pick a random value where you're going to start. Okay, this is my x start. You'll move this value by a slight, variation, let's say h, and you will test the next value. This will be x1, which is going to be x start plus the h value, and you'll compare these values of function. This was the value of the function at x start, which usually calls x0, and this is the value of the function at x1, okay, which means the next point. The hill climbing algorithm works this way. What it does is it will check the value that you found on the next. So it will check if the next value is bigger than the previous value. Okay? If that happens, if this condition is true, then it will treat this as the start value and then find the next value by nudging an extra h from there. Okay? x2 will be x1 plus h. So now I will find the value at this guy and compare this. If this value is bigger than the last value, which is false in this case, right? Because the value is now smaller. So this algorithm, okay, would want to now step back. So the climb is basically simple. It's going to start to climb these values step by step and see as you go up. The moment it fails that the next value is not really bigger than the previous one, it will automatically choose this guy and give you that's the maximum. That's just as simple as that. It's just like somebody's being lame and trying to find the maximum of this function. Okay? You didn't get it? I'll try to explain again. Okay? This is the function. We have it here. Try to move it like this. Let's say I am at this value. Okay? This is my starting value x0. I would not even expect this question to be on the midterm, to be very honest. It might be just like the algorithm's just kind of trying to guess the max. Okay? So you will not be probably asked for this on like a word problem. It might be just like a MCQ problem. So I would like, again, not to be worried too much about that either. So this is my x0 value. This is my function's x0. Okay, I move to the next step, which is x1. I find the value here. This is f of x1, right? And then I compare. Is f of x1 bigger than the previous value? Yes, it is. Then move on. Move to the x2 value. Make another one here. Find f of x2. And now compare. Is f of x2 bigger than the previous value that we found or not? Yes, it is, because in this case you can see that from the graph clearly it is bigger. Then it will say move on to x3. When you move on to x3 and you find out the function's value here at x3, you check the condition. Is the x3 value bigger than the x2? Well, no. So the hill climbing algorithm stops here. It stops here and it gives you this value as the supposed maximum. It's just an algorithm, I can't really tell you more about this than just telling you what it does, right? So on the exams, it's not going to be very crazy. Trust me. As a study guide, I was just basically asking you, do you understand what hill climbing is doing? Yes, I know it's just moving these x values until you find this new x value. You compare them to this condition. If the condition is true, you accept the point. If the condition is false, just stop the algorithm there. Okay? For people who are doing computer science, this will make a lot of sense. People who have never done computer science before will be a little bit difficult, but it's just what it is. Don't stress out too much on that. Okay, with that being said, I guess we're covered up almost the majority chunk of it. Now the things that are left is basically differential equations and finding the equilibrium solutions and checking their stability. So I feel for equilibriums, okay, it is fairly standard to find equilibrium solutions and go about it. How does everybody feel about those? Okay, if I was to ask you which one's more difficult, solving an IVP or finding equilibriums of a differential equation, because the math part is very easy. I will do both, of course, but but I want to make sure that I gauge what's more difficult for people. Just finding the IVP is harder, and solving it. Okay, we have a good idea, right? So I'll just try to explain that what's happening in like a very short, the hat thing. What is the hat thing for equilibrium? IVB stands for initial value problem. Okay. That's what we usually call it. The hat, I would not know what hat is like. A hat over a letter. Oh, that kind of hat you mean. Okay. It's a notation to find, yeah, I understand now. Got it. Awesome. So if you're looking at this and you draw this like that, right? This hat are you talking about? Yes, it's just a notation to represent the derivative. So don't really worry about this. If this is h, then this is that. That's just saying dh by dt. If h is a function of t. That's just a fancy way of writing the derivative. Okay. And those equilibrium locations of this, they could use notations, but you have to just be sure what they're asking for. Let me just clarify that first, okay? I'll show you. Okay. If you're given a differential equation, let's say I'm given dz over dt being 2z minus 4, let's say. Okay. If I'm given this differential equation and I want to find the equilibriums of it, if I'm trying to find the equilibriums of it, all we have to do is find where the dz over dt is 0. It's just that simple. Okay, I'm going to go back to we're doing equilibrium first, and then we're going to go back to the IVP. Okay, so this is literally how easy it is to do that. To find the equilibrium of this equation, you just set it equals 0. So 2z minus 4 equals to 0 tells you 2z must be equals to 4, tells you z must be equals to 2. So now they use this notation to say, okay, z hat is equals to 2 because that's like one of the equilibrium values. So they use this notation to describe an equilibrium. That's what they might use, right? But it doesn't really change anything. It's still an equilibrium, right? So if you know what they're asking for, you can give them this without the fancy hat, and you'll still get the marks, so you don't have to worry about it. Okay? So that basically means when z value is going to be equals to 2, this derivative, which you have for z, will be equals to 0. Okay, which means the value of z will not increase or decrease, which means it's going to be at its equilibrium. It's just as simple as that. Okay, so I can now come up with any sort of like weird expressions here and ask you to find the solutions or equilibriums of it. Okay, so like in this case, it was just a nice linear function. In the notes that I was going to show you guys, I have a little different one. Okay, I have it this way, which is a cubic. So I have a dy by dt, which is a y cubed plus 2y squared minus 15y, and I ask you for the equilibrium solutions of the differential equation, which means you have to just set it equals to 0 and do some algebra to find those y values, and I'm pretty sure you guys can do it. Okay, of course, I will show this up to you as well, but I want this question to be attempted by you on your own time. Okay, so like in, yeah, of course, then of course you have the lns and the other ones I'll show you here. So like in one of the problems on the exam was saying, let's say dn over dt is n ln n. Okay. If you have this, let's say, right, and you want to find out what the steady state of this expression, let's try to do that. The only way you want to do this, set this n times ln n equals to 0, where that would mean either n equals to 0 or ln n equals to 0. And whenever you're working with lns and you want to strip out this n from it, what you would want to do is raise both sides to exponentials. So e to the power ln n will be equals to e to the power 0. I literally take whatever that numbers are on both sides and raise them to natural exponents. Okay? And because of this, because e to the ln of whatever is just equals to that whatever, then I will be able to say that this is just going to be n. And e to the power 0 is just going to be 1. So the two possible values equilibrium are n equals to 0 and n equals to 1. How do you guys feel about this now? Good, right? It's just that simple. Sometimes you will have to come up with this expression and all those things. And to check now, this is the next step. Once we're looking at, you know, a complicated question, I would not go super complicated because the scope that they're testing you on and will not have a lot of this, but I'll show you, okay, just because you asked. But those equations don't even make sense. I'll just do it here. E to the power of n squared times ln of n minus 2 times n squared minus 4. How about this? Is this complicated enough? Of course, this equation doesn't make any sense, but I just cooked it up to make sure that you guys understand that this could be one of the questions that you can ask. So to find equilibrium states, you'll just put this equals to 0. Ln n minus 2 and n squared minus 4 equals to 0. That would mean either this equals to 0, which is not possible, as I just said. Exponentials are never 0, right, in the previous things. And then this would mean either this is equals to 0, so ln of n minus 2 equals to 0. That would mean ln of n equals to 2. And like I said, you would want to find n by raising both sides to exponentials. We'll get e to the power 2, so n must be equals to e squared. That's one of the steady states. And you said this equals to 0, n squared minus 4 equals to 0, n squared equals to 4, n equals to plus 2, or n equals to minus 2. So we have 3 equilibrium states here, where you have n equals to e squared, n equals to 2, n equals to minus 2. That's the answer. We're doing equilibriums right now. We're finding equilibriums of this equation. How does that feel now? It doesn't make any difference. If we have all these different things here, all we have to do is just make it equal 0 and solve, right? And that boils down to algebra after all. So not bad. Good. That's how we find equilibriums. Now to test the stability of an equilibrium, you have to look at what's the derivative doing at that location. Let's do that. I'm going to go over a simpler example like we did here. dz over dt was 2z minus 4, right? We had that expression here. So remember we found out the z equilibrium here with a fancy hat was 2, right? So now how I like to test stability, I'm going to teach you that, and it will be much easier to do all these questions with the standard form. Okay, what I'll do is I'll draw the number line again. Okay, and I will put down the z value that we found out to be the steady state equilibrium. So this is 2 that we have. Now remember, this is going to be representing the values of z. This axis is representing the value of z. And now all I want you to do is pick a value of z before this, pick a value of z after this, and figure out what dz over dt is for those values, okay? So we'll figure that out. Which value do you want to pick here? Let's pick z equals to 1. Why not, right? Is it possible? Z equals to 1? Let's pick it. So when you pick z equals to 1, so dz over dt as z equals to 1 will be equals to 2 minus 4, which is negative 2. Right? So that means the value of z will be decreasing. Right? In simple words, that's what it means, right? If dz over dt is negative 2, then z will be decreasing. Does everybody agree with me on that? Awesome, right? So on this line, if this line represents z values, decreasing z value means the arrows are going to go to the left. Do you see that? How I like use this convention now. If z values are decreasing, then z values should be going towards the left, right? Make sense? Easy peasy, right? Let's do it for the other point. Let's pick a point z equals to 3 here after 2. Let's do that. So now the dz over dt, okay, for this equation would have been basically 6 minus 4, which is going to be 2. So positive 2, right? So positive 2 means the value of z will be increasing. And for increasing, I would say the arrow goes in this direction. Does everybody see that? How I draw these new arrows that we work with? So now, once you're drawn these arrows for one equilibrium or multiple equilibriums like you're working with, what we have to do is we have to see if you have a steady state that has arrows going away from it, or an equilibrium that has arrows going away, like in this case, that equilibrium is unstable. Okay? And of course, if you have arrows coming in, then it's a stable equilibrium. Okay, that's very easy to figure out that way. Now I'm going to go back and ask somebody's asking a question. How do you know it's increasing? Because the derivative is positive. If dz over dt is positive, then I know it's increasing, right? So 6 minus 4 just means it's going to be positive 2, which means increasing, right? So you want to do a very rough graph for this example. Like, I'm trying to understand, how do you want me to draw a graph of this? Okay. But in general, okay, let me try to see what I can do you. So on the exam, that's why you will have to show if you want to see the stable. Another way of showing that here is to go and draw a different plot. I'll show you that as well. Your prof will probably expect this to be more appropriate, but I don't necessarily feel the same. So let's say we had this, and we had our z equilibrium to be at 2, right? We're just still working with the same example. So now I'm going to draw a rough sketch of the graph here, where this is t, and this is going to be z of t. Okay? So we have this information in front of us. I'm going to mark my equilibrium here. My equilibrium was equals to 2, right? So I'm going to have equals to 2 marked here, right? If you're asking about curve sketching, I don't think it's going to be testable on the exam. But I do talk about curve sketching in the calculus tool videos as well. So again, shout out to that video back. Right? So if you want to know more about it, I do that in that video as well. So just take a look over there. Okay, so now we're in this spectrum where we have. So now what I want to do is, because this is the equilibrium, I want to check the values of the derivative below the z value and above the z value. Okay, so I can pick, let's say I pick z equals to 1 here, and I check my dz over dt. And dz over dt would have been 2 minus 4, which is negative 2. So I know at this level of z equals to 1, the slopes are going to be negative. You see that? Does everybody follow along with this? How I pick a z value below the equilibrium level and test my dz dt. My dz dt is negative, which means my slopes are going to be downward sloping. Easy peasy, right? Nice. Let's go move on to pick a point z equals to 3. If you pick z equals to 3, then you test your dz dt, you would get 6 minus 4, which is 2. And it's positive. So at that level, the slopes are going to be positively sloping. So in this graph, what you would see is that the solutions are trying to diverge away from this equilibrium. They want to go away from this pink state. You see that? They're not coming in, and they're converging. Do you see that or no? The study guide example shows exactly the same thing. It will show you some solution that goes like this, right? Those solutions are diverging away from the equilibrium. That means that equilibrium is unstable. Exactly. How did I get 6 minus 4? You take z equals to 3, you plug it in there, you get 2 times 3, 6 minus 4, boom. If you have questions, ask me. Yeah, you're right. So because of you're kind of saying it in the opposite way. Well, equilibrium is stable if z values approach there is not necessarily the correct thing. You have to look at the other way, okay? So you have to see like if it is stable, then the z values will approach. By visualizing on the graph, you'll see it there. So the way to check that is to, if you want to check if they're stable or not, is to make sure you draw these graphs and have these lines pointing out there. So all you have to do is plug in the different values of z's into dz dt to find out if the slopes are positive or negative. Okay, you have to do it for each equilibrium state, above and below the equilibrium state. You check that out. If you see arrows are going away, that's unstable. If you see arrows are coming in, then it's stable. In this case, it's an unstable one. But how would you know it's positive or negative? I got these numbers. What are you talking about? I found that the slope is -2 here. I mean, it's a constant. What does that mean? Yes, it's a constant, but it's still a negative number, isn't it? So all I need to know if it's negative or positive, that's it. I don't care about the number. It could be any negative number, it's still decreasing, right? Exactly, that's what she said, right? So you use derivative plug-in that aren't the equilibriums. Yes, you will test the points that are above or below the equilibrium. Yeah, just like testing they used to do. That's why this is more easier to absorb than that one. Yeah, positive constant slope increases, negative constant slope decreases. Draw the arrows corresponding to that, and then you will see the picture. Right? Makes sense? If it's stable, then the arrows will be pointing like this. All the solutions are going to be like converging in. I really wanted to keep it till 5, but I guess people still have questions. So I'm going to try to go a little bit out, over this. But I want to make sure everybody gets what they need first. Okay? That's the equilibrium part, right? Well, it will have negative slopes, but the negative slopes will be on top. Right? If the negative slope's on top and the positive slope's on bottom, then you will have arrows that goes like this. Okay? So that's how we work it out in this way, right? I want to go over differential equations super quickly to make sure we're not just completely leaving that out. And of course, I talk about that on the IQ 9 video as well. So IQ 9 is where I solve IVP. And I guess IQ 10 was also a differential equation problem. Yeah, so I talk about those two. So I want to make sure you guys check those out too. But I'll show what's happening here. So an IVP is going to be made up of two things. It will be made up of differential equation plus an initial condition. Okay? So that's what we have to kind of like work our way out on this, and that's where the important part is, okay? Now, an IVP, an example of an IVP is like this. If I say dv over dt is equals to 2, and the initial value of v is 5. This is an IVP. Okay? I will share the links for the playlist again on both Messenger and Discord. So if you guys need to go access those videos again, you can do those, right? And IVP stands for initial value problem. Okay, initial value problem. Okay, that's what this is. So it's going to be composed of a differential equation alongside an initial condition. So here, this is my differential equation. This is my initial condition. To solve an IVP, it's always guess and check. Okay, so now you tell me You tell me a function v whose derivative is 2. What would that function be? What would that function be? 2x? Everybody agrees it's 2x? Because then you would take this thing, right? So you said v is going to be 2x, right? Nice and easy. No problem. I say the vx is going to be 2x plus 5. Right? Do you see, if I say 2x plus 5, it doesn't really change anything. The derivative is still going to be 2. The positive constant does not, harm you at all. Do you see that? Does everybody see that? Like 2x is a valid answer, nice, but 2x plus 5 is also valid, isn't it? Because that also still has a derivative of 2. And the reason, what's the x for? It's a function, right? Oh, it should be a function of t, my bad, because I define it with t, right? This is the function t, so it will be a function of t. Thanks for pointing that out. Right? That'll be more appropriate because we're taking the derivative with respect to t. So it'll be 2t plus 5, right? So the original function would have been this so that the differential equation was satisfied this way. Okay? Does it also satisfy the initial condition? Try to check it out. Okay? If I plug in 0 here, I get 2 times 0 plus 5, which is just 5. So that indeed checks with this, right? And yeah, I'm going to go over that example too. Just going to make sure we redo that. Okay? This is how we work it out on a very simple scale. Now I'm going to give you the 4 basic forms that they will be asking you questions on. They cannot ask you questions. Well, yeah, you can use antiderivatives, but in this particular course, they are not allowed. Okay? Guessing and checking is the one that you have to focus on for now because this is a part of Calculus 1. Having an antiderivative on the exam will just make you lose marks. Okay? Because it's not taught. Of course, if you want to do it for yourself, you can do it, but don't show it on the exam though. Okay? So now the 4 forms they can ask you here, where if dy by dt is a constant, let's say 5, if dy by dt is a linear, let's say 6t, let's say, if dy by dt is going to be a constant, let's say, 2 times the y value itself. Okay, so pay attention to that. This is slightly different. The antiderivatives that you are being learned is basically antiderivatives of basic power functions. Okay, and the process of finding antiderivative is basically given after fundamental theorem of calculus. So for this particular exam, I would not recommend you writing the solutions in an antiderivative way because that's not testable in this particular case. But if you know how to do it, and you will know, of course, in Math154, that's all we're going to do. Math154 is exactly going to be based on antiderivatives and all that stuff. So make sure just try to keep the answer in the scope of what they taught you, especially when it's doable in that scope. So, it's easier that way for them, both of you guys to get marks and for them to mark them as well. So that's the 3rd form. The 4th form is to have, dy by dt with a function of t, right? So let's say we're going to call this function of t 2t with a y. The 3rd is called autonomous equation. Okay? Autonomous equation is where you see the variable y just comes back in this picture. In this case, it was a constant. In this case, it was the t variable, which makes sense. But now when you have this whole function repeating itself, you'll have these 4 forms that you can work with, okay? The first form, if I'm going to have initial values with them, so I'm going to call v of 0, let's say equals to 2, y of 0 equals to 3, y of 0 equals to 6, and I'm going to just call this y of 0 being equals to 1. It's 2t times y. Okay, I'm multiplying it with y. My bad. Okay, So now solutions to a differential equation that has to the IVP that is just 5, you know the solution is going to be 5t plus 2. Okay, it's very easy to guess for a solution to be that way, right? Because of the initial value, and it works out. You can verify this result as well. You can go back and take the derivative of this expression. You know the derivative is going to be 5. And you can also check the initial value. It's going to be 2. So essentially what you're doing is you're taking the antiderivative and adding the initial value to it. Okay, the antiderivative is just going to be 5t, and then you just add the value to there. Okay, here, if I was to ask you what's the function whose derivative is 6t, can you tell me a function whose derivative is 6t? Can someone tell me a function whose derivative is 6t? Yes, that's going to be 3t squared. And the solution to the IVP is going to be 3t squared plus the initial value. Okay? Make sense? Does everybody see how that works? And you can, of course, go back and verify this by taking the derivative and checking the derivative is going to be indeed 60 and making sure checking the initial value. That's also going to be 3 there, right? Now, these questions become a little bit interesting, okay? Whenever you see a dy by dt having a y there, yes, it's all guess and check, but it's not just like a dumb guess. It's a more educated kind of guess that you're making there, right? You're looking for a function whose derivative is 6t. So it's not just any function, of course. It's going to be like 3t squared or some limited ones, right? And that way we can figure it out. So that's that. Now these equations, when you have 2y, the same variable repeating here, the y comes here. The solutions, yeah, you can do the antiderivative in your head and just not show it and pretend that you just guessed it, right? So that also works. But don't explicitly say that you're taking antiderivatives on the exam, because somebody probably won't like that. Okay, so with that being said, that's done. Solutions to exponentials, like in this case, would be e to the power of that constant 2t. That's how these solutions look at. Whenever you see a y there, okay, you're going to find the antiderivative of this function and put it in the power. Very simple. Okay, so antiderivative of 2, what would that be? Can you tell me a function whose derivative is 2? Yes, the function is going to be 2t, right? Does everybody agree with me on that? Tell me a function whose derivative is 2. 2t. Does anybody else have any other options? 2t, right? So just take the exponential and plug that 2t over there. Okay, that's how we do it. T squared does not have the, so the reason why it has an exponential is because of it's a y, and I'll tell you why that happens. But all you have to do is, when you see a y there, you have to take the antiderivative of this function, okay, and take it and plug it in the place of the exponent here. So like in this case, that happens. And what about the initial condition? What does that do? Yes. Like I would go on to add 6, right? But the addition would not properly work, okay? When you're working with autonomous and exponential functions, you want this 6 to be here, multiplied in the front, right? The reason why I multiply, because this is the only form that matches up the solution. I will not be able to explain you why this is the solution just yet, because you're still supposed to learn the contents of lecture 24 and 25. Okay, so once we're done with those, we can come back to these and tell you exactly why the solution is the solution. But for now, just, you know, take it with like a chill pill and just assume that that's what's going to happen. So that's why I have this example here. So I'm going to show you this again in this context as well. So see, there's also a y here, right? So I know the solution will be an exponential solution because I see a y, right? Easy. And now all I have to do is look and find a function that is derivative is 2t. Can you tell me a function whose derivative is 2t? t squared, right? So I'm just going to have a t squared sitting here. Okay? Makes sense? So start by having an exponential because you see a y. Look what's in the front of y, find an antiderivative of it, plug it into the exponential of the power, right? Like in this case, we had a 2. So the function whose derivative was 2 was 2t. So I just literally had the exponent to the power of 2t. And then I had 2t here, so the function that is the derivative of, has a 2t is t squared. So I'll just put it into the power of that. Right? So it'll be e to the power of t to the power of 2. Yes, exactly, e to the t squared. So that's this, right? And what about the initial condition? Because it's an exponential function, right? An exponential function will always have a 1 there, multiplied in the front. Exactly. You got it right. So now let's do one tough problem and call it after that, okay? Let's do one IVP that's a little tricky so that we make sure we understand everything, okay? So now I have dy by dt. It's going to be 3t to the power of 4 times y. Okay, and I'm going to give you the initial condition here, y of 0, to be, why not? Okay, let's do that. So now when we have it in this expression, we know this is going to be an exponential solution because of the y. Okay, so we have an exponential, and now we're looking for a function whose derivative is 3t to the power 4. Can anybody tell me a function whose derivative is 3t to the power of 4? This will be a little tricky, so take your time, okay? I need a function whose derivative is 3t to the power of 4. Okay, I know somebody's finessing their you're almost there. Yeah, 3 over 5 times t to the 5. So people have agreed it's going to be 3 over 5 times t to the 5. Okay. Try to see. If you take this function and take its derivative, do you get 3 to the power 4? Yes, you do. Right? So this, how did people find that quick, is because they've been doing it so long. Don't worry, you'll be fast enough too. If you practice enough, you'll get there. Okay? Yes, the power of antiderivatives, yes, you might say. Okay? Well, just saying that whenever you see this kind of thing, it'll take some time, but you'll get to that number. Does everybody see that now? Okay? It's that easy. So we got that thing, and now all I have to do here is just have the initial condition multiplied over there. Okay, what do you want to wait for? The rule is basically looking at this function, okay, and saying it's going to be an exponential. And then the next thing I want to do is just have this here, and then work it out in this format with this function. This function is the function whose derivative is seen in this equation. Well, let's see if you want to add 68 to this. Let's see what happens, okay? Let's try to check. That could be also a valid solution. I'm not going to dismiss that, okay? But it'll be more appropriate to have that 69 just being multiplied in the front. It's easier that way. So if you propose the solution is e to the power 3 over 5t to the 5 plus 68, right? If you say that this is the solution, this is one of the alternate solutions that one of the persons represented, which is nice, but we have to verify this is a solution, right? So how do we verify? We're going to check if the differential equation actually looks like this or not. So I'm going to take the derivative of y with respect to t. I'm going to get e to the power of 3 over 5t to the 5 times derivative of 3 over 5t to the 5 will be 3 over 5 times 5t to the 4. Okay, and then plus 68 will just be 0. So now this leaves me with the derivative dy by dt. That looks like 3t to the 4 times e to the power of 3 over 5t to the 5. That's what it looks like, right? That's what it looks like, right? So I know the initial condition will be fine. If you plug in y of 0, you will get e to the power 0 plus 68, which will be 69. Nice. The problem is that the differential equation is not satisfied. The differential equation is going to be 3 to the power 4 times y. Is this 3 to the power 4 times y? No, right? Do you see why it's not? Because from here, if I was to substitute e to the power 3 over 5 t to the 5, that will be equals to y minus 68. So this differential equation would just be dy by dt with 3t to the power 4 times y minus 68. So that's wrong. That's not what the equation was given to us, right? Make sense? So you have to see that the equation, its derivative and the initial value both make sense. Right? Now I'm going to go and verify the one that we picked was making sense, okay? We picked y of t to be 69 e to the power 3 over 5 t to the power of 5, right? That's what we picked. So now let's check its derivative. When you take the derivative of this function, what do you get? You get 69 e to the 3 over 5 times t to the 5 times the derivative of 3 over 5 t to the 5, which is going to be 3 over 5 times 5 t to the 4, which just happens to be 69 e to the 3 over 5 t to the 5 times 3t to the power 4. And now you can clearly see this is y, because that's what our y value is, right? So that makes my differential equation 3t to the power 4 times y, which makes perfect sense because that's what is supposed to be given in the problem. Does everybody follow? Right? Now it seems to be easy. And now you want to check the initial condition. Plug in y of 0, you get 69 times e to the power 0, which is 69. So that also matches up. So this is more appropriate. Okay. I'm trying to see. Yeah, this is the left and the right thing in the lectures, okay? All you have to do is just verify the results. You don't have to be fancy writing, oh, the left side is this, the right side is that, boom, they're equal. You can do that if you're like kids in high school, but nobody needs that. As long as you can tell them this is matching up, so it's all good. Okay. Nice and easy, right? So that's all what you need to do for this. And now that we're like almost on the end, I want to show you some of the examples. I want to give you some tips on this so you can attempt these yourself. I'm gonna erase this mess that I made here. Okay. So the first question is going to be based upon finding max and mins and all those things. Second one is going to be an optimization problem. Third problem, now you guys know how to solve this problem. Okay. I want to just walk you through it super quickly. This is going to be a y cubed plus 2y squared minus 15y. So it's a polynomial. Okay. We want to find the equilibriums of it. So you would just literally have to find out of this solution. And then you have to figure out equilibriums part, is it stable or not? So you know how to find equilibriums are stable or not. And you also know how to find the solutions are going to go if you initially start at this point. Okay, so give it a shout, you'll be able to find it. This IVP, can somebody tell me the solution to this IVP right now? So we're given dz over dt is 2t minus 5. Can you tell me a function whose derivative is going to be 2t minus 5? T squared minus 5t. And what about this little guy there? You want to add that to that thing. Exactly. Does everybody see that? Right? You guys got it in like a nanosecond. So that's pretty good. You guys are very quick at that. I'm pretty sure you guys just took the time to type it. So why the 5t? Because tell me a function whose derivative is negative 5. You tell me. Negative 5t, right? So that's what you're going to do here. And then you're going to add that initial condition there. Remember, this equation does not have a z there. If this equation had a z there, then you would have to do it in a different way. Okay? I'm going to be making an interesting problem here. Let's see if you guys can do it. Okay, if you guys can do this one, it will be very easy. Let's check this if you guys can do this. dz over dt is going to be now 2t minus 5, but with a z multiplying there. How would be the solution of this guy look like? Now I have a z there. So you know the solution is going to be an exponential. You agree or not? It's going to be an exponential. And the power of the exponential is going to be, the function whose derivative is given right here. So the function whose derivative is 2t minus 5, everybody's nailing this. So it's pretty good. I'm very happy. This is going to be just t squared minus 5t. And the initial condition is just going to be in the front. Okay? Just going to be 2 times all of that thing. I'm pumped. You guys are doing great. Right? Very easy. No problem. And that's how we finish it off, this problem here, right? And somebody had a question about how do you find the derivative of question 3? This one? Why would you want to find a derivative of this? It's okay, don't worry. If you're not on the bandwagon who knows this, it's okay. Ask questions. I'm here for you. Don't worry about it. I'll do the exponential part in just a thing. So you were asking about how to find the derivative of question. Oh, the function for that, not testable. Okay, don't worry about it. The question that will ask you for finding equilibriums, they cannot ask you to find solutions of those. It will be a nightmare, okay? And you will learn all of this in Math155. So don't worry about it. You'll just be patient. You'll be in the misery of learning how to find solutions to that equation soon. Okay? So don't worry about that. The exponential part, remember how we talked about it. Whenever you see a z here, okay? Whenever you see a z here, you know it's going to have an exponential because the z is the function that's repeating here, right? So we know there's going to be an exponential for sure. So you put up down there. The power of the exponential will be the function whose derivative is going to be this guy right here. So the derivative should be 2t minus 5. So the function should be t squared minus 5t. So we just put it up there, right? And then the initial condition is just this initial condition is going to be multiplying over there. Right? The 2 is basically the initial condition that's given here. And we know we always multiply by initial conditions when we're working with exponentials. And we always add if we're working with non-exponentials like in this question originally. Okay? So to verify, you just find the derivative, what we just wrote down, and make sure they're the same. Yes. And you also find the initial condition and verify if that's the same or not too. Okay? Yes, so this question was different, and this question is something that I made right now on the wing. Okay, so just, challenge you guys, but you seem to, beat it off, so it's very good. So see y or z, it's not just y or z, it's going to be this variable. If this variable, the prime variable of the differential equation, shows up here, okay, if it's z, then z, if it's, I don't know, q, then if it's going to be q here on that side, right? That shows up, then you know it's the exponential form. Right? That's where that is going to be. So this is that done with this. Yes, we don't have to use quadratic equation. You guys are smart at this. If you factor out y, then you will see a quadratic which is also factorable. Yes, you can ask me questions now because we're done with the content. And how would I give answers to question 3b? You would know how to find them if they're stable or not by using, so I want to make sure that we're working with this part. I already explained you how we find the equilibriums are stable or not. So you'll draw the graph, you'll put these equilibriums on there, and then you'll check it out in that format, right? So I would still want to leave it to you. I will post the solutions to this, so it will make sense, but I do want to ask you guys to give it an attempt first. Okay, we're working on this. The agenda was not to work on this because I want you guys to work it on yourself. But you guys forced me, so it's okay. We'll work through these two problems, but you have first, second, and then fifth and sixth problem to work by yourself. And of course, check the solutions afterwards too, right? So with this, I think we are done with the questions. I'm just going to put this YouTube video on YouTube, review right away. And the moment it gets processed, you guys will have the link, okay? So you'll have it, and right now what we're going to do is we're going to let people ask some questions if they have. And, so if you guys are asking what you should be spending time on right now to study, make sure you practice as many questions as you can. Okay, you know everything. Now the time is to just grind those extra little, hairs here and there to make sure they're all find out. If you have any questions while you're working on some problems, you know what to do. Take a picture, send it over to me, and I'll be more than happy to help you out with that, okay? So that's that. And the extra questions, I would say fix the questions that you are doubtful on first. So go back to the OQs, go back to the IQs, make sure you know them 100%. Okay? I'm sending you these 6 questions, so practice these 100%. And that should be it, because you don't have much time anyway, so you have to relax too, right? So don't worry about practicing crazy amount of questions. Just do what you did, but with more proficiency. Try to use Desmos this time. Try to make sure that you're able to type things in and extract information from Desmos, because you want to save time on the exam, right? I will post the answer key and the questions both on Discord and Facebook, okay? So don't worry about it. This is coming up right after this. You guys are very welcome. I will let the participants now share the screen if they have questions and they want to ask. If you guys want to stay along, stay here. I don't have too much time. I'll probably be here for another like 5, 10, 15 minutes. But I try my best to answer all the questions. And from that point onwards, we can, open the stage to you guys. So I think you should be able to share the screen if you have a raised hand. Feel free to unmute yourself and talk to me too.
Hi, so I have a question from lecture 21. I'll
Okay,
just share the screen.
sure.
So it's this one.
Mm-hmm.
I'm not really understanding it.
So this particular problem is based on the flow diagram, okay? And did you get the differential equation from it though? My point is that,
Yeah, I understand
right?
this.
That's
And
the
this
part, right?
is the K meaning constant or?
So in this case, Ka is a constant, okay? And K happens to be the value that you raised your, your function to. So that's where it's going to be. Now in this particular case, they've chose that if K equals to 1, what's happening, and and all that stuff that we're looking at. Let me try and add this window to the recording as well, so that people can see what we're looking at. Now it won't let me. Okay, because of privacy issues, it won't let me share your screen to the people in the recording, so I might just end the recording at this point and just